Okay, I want to do one last calculation with this problem, and that is to find the factor of safety in a different way. It's going to be defined in a different manner in the sense that, well, it'll still have the same equation, but instead of using the net pressure diagram, we're going to use the total pressure diagram. So in other words, if you remember what we had last time, we created, well, let me show the two different, This is the total pressure diagram. And this is the net. We showed you how to do that. So in this particular example, we used the net stresses, these net stresses, to find the factor of safety. So we had to find the areas of this region here. And now we're going to use the total to find the factor of safety, and we're going to get a different answer, I'll tell you in advance. But what do we have to do with the total? Well, now I have to create new shapes here and create forces from those shapes. And then find the factor of safety from that. So let's take a look at it. And so I broke this up into these shapes, and we found the areas. The areas are given for each of these shapes. So there's 13.5, 20.3, 108, 69, 132, 13.5, 20.3, 108, 69, 13.2. So we use those areas, and now I'm going to use this free body diagram. Again, I'm going to take moments about the anchor point there. And so I have, for my resisting, I have simply the 132 times 5 meters. That's the resisting. And on the kick out, I've got 1, 2, 3, 4 of them. You can all do this. I'm not going to go through it, but that gives me these 4. That's the numerator, 132 times 5. And then working out this expression, my factor of safety is 0.74. Now that contrasts with the one that we got for the net stresses, where we got a factor of safety of 0.06. Now neither one of them obviously is acceptable, but you will get different results. And here's the reason, is that the factor of safety, again, is not a theory, it is a definition. And depending on what organization you work for, they're going to try to put safety into this in different ways. And so you need to, when you're working, you need to follow the methodology that that your organization uses. Now, more commonly is to use the net, but that's not necessarily required. Okay, so you might say, well, look, since an anchor does pretty well, why not put in more anchors? So in theory, we could build a wall that looks something like that, put in a bunch of anchors. That's going to give us a much more stable wall. Now, as I've shown it, this is a little bit difficult to construct, but we can make a tie-back wall, which is commonly done, which has many anchors. And how do we construct a tie-back wall? Well, here's my original situation. I can take the wall, basically put it in place, and then we drive the wall or push the wall into the ground. Once the wall is in the ground, then we're going to start to excavate downward. So we may excavate a little bit and then insert an anchor. Then we excavate a little bit more, insert another anchor. Now, how do we insert the anchor? We drill at an angle. You can see this is at an angle. And we grout at the end and then insert a rebar for instance, and that gives us the anchor, and then we basically tie it off here at the wall. And then we excavate some more, and then we do some more. Put in the grout. The grout is usually like a cement, and then you can test these by pulling on the anchor, make sure everything works right. So you want to make sure that the anchor is well away from the wall. And so if you draw a 45-degree line, for instance, that's often used, and you take and you make sure that the anchor is well outside that 45-degree line. You don't want the anchor in here because in this region, because that's too close to the wall. It's got to be away from the wall. Otherwise, that portion of the soil will move and the anchor will have no impact. And then we talked about a soil nail wall where we put in soil nails. But notice one of the reasons I'm saying this is a contrast with these two situations, in that an anchored wall sort of looks similar to a soil nail wall in that we're drilling or driving into behind the wall like that, but the anchored wall is different. It's grouted in at the tip. It's meant to anchor the rods here. On the other hand, the soil nails are more of a reinforcing thing. Although they look similar, they're meant to, there's no grouting at the tips. They are meant for creating sort of a reinforced region, reinforced earth region. So this is more like a gravity wall. This is more like an anchored wall. I'm not going to go through how we analyze these walls with many anchors. That's another issue, but you're learning the basic concepts of wall design here, and tie-back walls are another issue. I'll also mention that you can have a braced wall. In other words, suppose you're digging a trench and you need to support the trench. Well, what you can do sometimes is simply brace across from one wall to the other. You have two walls here, one wall, another wall, and maybe they're not that far apart. You can simply brace across the walls. It's commonly done. You have to make sure that you have room to work in the hole. That's an issue, though. So a braced wall is another kind of wall. We're not going to cover that one here. And I'll just make a little comment about the structural engineer. And that is, and I want to make the comment about design the retaining wall. Okay, that word or that phrase means two completely different things to different civil engineers. To a structural engineer, design the retaining wall means one thing. To a geotechnical engineer, design the retaining wall means something completely different. To a structural engineer, designing the retaining wall means to, for instance, design the thickness and shape of the wall. We'll focus on that. What is the concept for a structural engineer to use? Well, you analyze, or a structural engineer would analyze it like a beam. In other words, we've just talked about getting the earth pressures on an anchored wall. For instance, we just did that. So what are we talking about? We're talking about, there's my wall. These are my earth pressures. And what do we do with that? and there's also there's also the anchor force there. But what do you do with that wall if you're a structural engineer? Well, you take it and you rotate it. And in other words, instead of this, you rotate it 90 degrees and you get that. Then what? Then you put the the stresses on it, and the stresses may look like, I'm just sketching something here. Stresses and the loads may look something like that. And now it looks like a beam problem. So in other words, you've studied beam analysis, so you can draw shear and bending moment diagrams for that beam and then just simply analyze the wall as a beam. That's what a structural engineer would do. So that's design for the structural engineer. Design for the geotechnical engineer is what we looked at before, which is, we designed our wall, and we tried this wall, and well, that wall had a very low factor of safety. So that's not good enough. So what does the geotechnical engineer do? The geotechnical engineer is going to make the wall longer. Typically is what's going to be done, for instance, could be done. Or more anchors or something like that, however, different approaches. That's what we mean. If the geotechnical engineer is going to design the wall, that means, how long is the wall, or how deep is the wall going to go, and where is the anchor going to be, and what are the earth pressures. That is, and what is the factor of safety. That is design for the geotechnical engineer. So just to be aware that a structural engineer and a geotechnical engineer can hear the same phrase, and to them it means things completely different. This also is the same with foundation design. When we get into foundation design, you'll see that foundation design, to design the foundation, you're given that instruction. You give that instruction to a geotechnical engineer, it means one thing. You give that same instruction to a structural engineer, it means something completely different. Okay, I just want to, just going to work a couple more examples very quickly. We've already done these pretty much. But just another example here, I've got another wall. It's 8 meters, 6 meters height. It's 4 meters width. It's gravel on both sides. I've got the water table there and there. Here are my unit weights. There are my earth pressure coefficients. And we're going to start with just draw the stresses to compute overturning. Again, now here I only have one soil type. So if I only have one soil type and I have the water table there, then my depths of interest are going to be 0 at the top, 6, and 8. I don't have to do 6 plus and 6 minus, or 6 minus and 6 plus, however you want to say it, because it's just the water table. There's no discontinuity there. The slope has a discontinuity, but the value doesn't have a discontinuity. So we only need 0, 6, and 8, not 0, 6 minus, 6 plus, and 8. Why? Because it's all one soil, and we only have one Ka, so there's no reason to put 2 in there. And then we do the passive region, which is in passive region is over here, 6 and 8. And we do our sigma V's, 6 dry, then 6 dry plus 2 saturated. Over here I've got 2 saturated. The pore pressure is 0 except at the base of the wall. 0 base of the wall. Sigma V minus U gives us this column. And then again, what do I have? This is the active, this is the passive. They're two different. And then for sigma H prime, I go Ka sigma V prime. Over here, I go Kp sigma V prime. And then at the end, sigma H is sigma H prime plus U. And then we plot those results. So the sigma, in other words, we plot the sigma H here. And there's our plot. The active, the passive. Now what do we do here? Well, we've got to put on the water. Where does that come from? That 19.6 comes from right there, 19.6. 19.6. It's the water table is at the same level on both sides. It's 19.6 on both sides. So for overturning, we have to put in that water. Why also? Because it's gravel. Gravel, the water comes out of the gravel to give us that water pressure at the base. If the soil were clay or silt, we wouldn't put that in there. Then we also have the weight of the wall, which you can all do. So this answers our problem here. So our resisting moments, again, we take moments about that point, and I'll show you how we do that. Again, we take this, we break it up into triangles and rectangles, we get the areas, you can all do that, I'm not going to go through it. We put on the forces. So this is our water pressure force, these are our actives, that's our passive, that's the wall weight. And take moments about that point there. And we get our overturning moment is that, our resisting moment is that. The factor of safety then is that 2.21. So this wall passes. I have factor of safety greater than 2 in this case. So this design works. Another example, again, these are just practice. You should go through them to get the exact numbers. I've got gravel, I've got sand, then I got sand, I have the water table. Here, similar to the previous wall, except now I have sand. It's the gravel sand interface. What does that mean for me? Well, okay, again, here are all the soil properties. And I've also given you a coefficient of friction there. And now what do we do? Now, because I have gravel here and sand here, I have a discontinuity in these wall stresses. So I have to have a 6 minus and a 6 plus there, and 8. So I've got 6 and 8 there, 6 minus 6 plus and 8, 0, 6 minus 6 plus and 8. And then you can all compute these. So I got my sigma v, u, sigma v minus u, and then of course what do I have to do when I get to the sigma h prime? Notice a handy thing to do, I haven't shown it here, but maybe I'll just do it real quickly, is that it's a good idea to put in a line there. That line, what does that do for us? That separates out the gravel and the sand. So in other words, I have, let's put it right here, this is the gravel and this is the sand. So once we know that, what does that mean for us? That means that in the gravel, I'm going to use Ka in the gravel, 0.4. In the sand, I'm using Ka in the sand, 0.6. So don't forget to use the correct earth pressure coefficient. And again, this is the active, this is the passive. So when we get down here, I'm going to use the passive coefficient, 3.8. Again, we create our stress distribution, and it's a sand, so we have the water pressure at the base. And then I'm not going to go through this, but we get our areas. I have a 1, 2, 3, 4, 5. So I get A1, A2, A3, A4, A5. And again, I'm going to take moments about this point for overturning. And what do okay, first of all, remember the 78.4 comes from this portion of it. That is going to be A5, 78.4. Then, how do I know what this is? Well, that is going to be the 832, which is there, minus the 78.4, which is there, so I get 753.6. What am I worried about? I'm worried about, I want to have equilibrium in the vertical direction, so the sum of these two has got to be equal to that. And I know that that 78.4 comes from that. So, again, that's how I get that particular value. But when I'm taking moments about this point, that doesn't exist because I only have the water pressure. Why? Because I have liftoff of the base of the wall from the soil. So I only have the water pressure for analyzing the overturning. So as I said, for overturning, use only the black colored forces because the wall lifts off the soil base. Take moments about A. So using only the black here, I get my overturning and my resisting right there. And then for sliding, use only the horizontal forces because sliding, it's not moving vertically, so we don't use the verticals. So there are my horizontal forces right there. And the last one that you have to pay attention to is the friction at the base of the wall. How do I get the friction? Well, I'm going to use the force here that basically in a sense is the contact force between the sand and the wall. That 753.6, I use the coefficient of friction 0.35, gives me the frictional resistance of 263.8. So you want to make sure that you only use this one in computing the frictional resistance. Why? Because the 78.4 represents the water. Well, the water doesn't have friction. It doesn't resist friction. So we just stick with this one. So the factor of safety of overturning is 2.29. The factor of safety against sliding works out to be 1.38. Well, what does that mean? You need to have at least one at 1.5, even preferably 2, depending on the situation. And so it fails. The wall fails. What do? Well, you can embed the wall. You can make the wall a little bit wider and heavier. You have options, but you have to redo this design. It doesn't work. Okay, I want to make a comment that what happens if the water table on both sides of the wall is not the same? In other words, what if the water table is here, over there, and over there it's there? Well, it's a little more complicated problem, but for our purposes, we're going to do a little simplification, and we're going to have, let's say this is 5 feet here. So I'm going to take the water pressure there as 5 times 62.4. We're doing English units. And then this distance here is 31, so that's going to be 31 times 62.4. So what do when we create a little trapezoid here that's going to represent the water pressure, and then we have to find the area of that trapezoid to get the force. So we have stress. This is our stresses. We have to convert that to a force by taking the area. And that means, of course, we're only going to use that when the wall is in gravel or sand. So in other words, when the base down here is in gravel or sand, that's what we want to do. And then I want to make one more comment. This is an important one for you to learn. And that is, I want to do a comparison of dry versus saturated soils. What are the earth pressures under this situation? So we're going to keep it real simple. Let's just say I've got 2 walls. There's the first one, case 1. This is the second one, case 2. Case 2, I've got dry sand. Case 1, I've got saturated sand. So I'm going to have, there is my water table there, and this is completely dry over here, so there's no water table. So it's the same sand in both cases. This is the gamma saturated, gamma dry. Ka is 0.5. We're just going to look at the active stresses here. So for case 1, I've got 0, I've got 10 feet. Case 2, I've got 0 and 10 feet. So 0, 10, 0, 10. Both of these are active only. So it's saturated, so this is 10 times 120. This is 10 times 110. We have a pore pressure, in this particular case, 10 times 62.4. There's no pore pressure because it's dry for the second case. I get my sigma V prime as sigma V minus U, so I have 576 for sigma V prime. For the saturated condition, for the dry, it's 1100. But what happens? I use the 0.5, the Ka. So I go 0.5 times the 576, 0.5 times the 1100. And so I got 288 and 550 there, but what happens what do I have to do? I've got to add in the pore pressure. So I take the 288, I add in the 624, I get 912. 550 plus, that's 0. So I end up with 550. So when I'm all done, when I look at the stresses, what do I see? I've got 912 for the saturated case. Over here, I've got 550 for the dry case. Obviously, what do we see? We see that the saturated condition is much worse. Water causes a large increase in the active stress. So here's the thing. We don't want water to be retained by our wall. This is an important point, because what happens is, if it's raining hard and things like this, is when walls fail or can fail, because what can happen is the rain comes down and what does it do? It fills up the region behind the wall, or it can fill up the region behind the wall. And if it does that, then we end up with saturated soil behind the wall, and we end up with a much greater earth pressure. And if the wall hasn't been properly designed for that earth pressure, the wall can fail. So we don't want that. So what do? One solution is to prevent water from accumulating behind the walls, to make drain holes, or ensure that the water gets out. So make sure the wall is free draining. Some walls automatically sort of have drain holes. Others need to have them in there so that the water never accumulates. It comes out the holes. So it's an important point. Make sure that you have good, what we call good drainage behind the wall, that the water can come out. And let me just, why? Because, here I'm showing a dam here. You don't want your wall, in a sense, to have the extra burden of holding back all of that water. That is what we want to avoid. We don't want to build a dam. I mean, in a sense, we're building a dam, but we're holding back soil, but we don't want to hold back both the soil and the water if we can avoid it. Sometimes it can't be avoided, but... Now, I'll just make a little comment about slope stability, because it's somewhat similar analysis to what we're doing here. And that is that if a slope is going to fail, sometimes it can take this form of failure where a little wedge of soil comes off the top. A little wedge, it could be a significant wedge of soil comes off. And this analysis is very straightforward in a sense. We have the weight of that wedge, we have a frictional force, and we have a normal force. It goes back to an analysis that you did in your statics course, your early days of statics. Let's make that comment. We're not going to look at it in detail, but I will make some comments here about slope stability. And that is that your typical hillside, so why is there a hill to begin with? Well, it's because most times is that there's rock underneath. The hill is rock with soil sitting on top of the rock. So it's usually not just a pile of soil, even though you may see soil. It's not a big pile of soil. There's usually rock underneath it. So the rock is normally has a slope to it, and then there's a little mantle of soil above it. This is sort of a typical situation. And I'm going to do some oversimplification, but you're going to get an idea of what can occur for different soils in concept, in a sense. And that is, what happens is that it rains. Most of the landslides, a lot of landslides are associated with rain, because this water that comes down can be substantial. Now, it might not happen right during a rainstorm, but it could happen after a rainstorm, and it could be because water is in the soil. Now, let's take a look at different situations where the soil is clay, where the soil is gravel, soil is fine to medium sand. So let's look at three different situations. Let's look at the clay one first. Well, what do we know about clay? If this soil is clay, well, what happens? The rain comes down, and what do we know about clay and water? Well, it's tough to get it's tough to get water out of clay. It's also tough to get water into clay, in a sense. And so, if this is clay, then the water is going to come down and it's going to run right off the top and go down. And if that's the situation, then there's going to be, for this situation, I'll enhance this in a minute, but what happens is it has no effect then on the slope. The rain, in this case, the rain does not cause a slope failure because it doesn't affect the soil. Let's take the situation where the soil is gravel. If the rain comes down when the soil is gravel, so it's raining, well, now I've got gravel. Well, gravel has very big voids. So what happens? The water goes through the gravel, goes right through, no problem, because there are big holes in there. And it goes and it hits the rock, and then what? It just rolls down the side of the hill on the base of on the surface of the rock. And what does that mean? Well, again, the water doesn't really have any effect because it goes right through and down the slope, doesn't do anything. But now let's take the situation where the soil is fine to medium sand, for instance. Now what happens? It rains. Well, it rains, and that means what? Well, some of the water is going to go off the top, but water can get into sand. And what happens is, if it rains enough, that the water, some of it's going to run off the top, but some of it is going to go into the sand. Now, the sand has voids that will accept the water, but those voids are not as big as they are with gravel. The water doesn't move freely, so what happens is some of it comes off, but then what do? We end up, the water sort of gets stuck in here. It wants to go down, of course, because water wants to go downhill, but it really can't because it's just not permeable enough. Can't run through it like it does with the gravel. So what happens is that we get this soil becoming saturated. It gets very heavy. It wants to go down, but it can't, like I said, because unless it takes the soil with it, basically. So the concept of this is that you can sort of see that when we have a heavy rainstorm and we start saturating this sandy soil, that we could get a slope failure simply because the soil becomes heavier and it wants to move downhill. The water wants to move downhill and it takes the soil with it. In a sense, it's your classic weight on a ramp problem that you did in your statics class, and we can analyze it. Just as I was saying, we got a weight here, we have a normal force, we have a friction. We're not going to go through the details of that analysis, but I want you to be aware of the impact of water rains on both slope stability and our retaining walls, we like to have these free draining soils. That's our best bet. And let me make one other comment. So what I'm talking about the clay here, and that is that now, if the soil is clay, what can happen? I've shown you an ideal case, but it's rare that our ground surface is straight like that. In reality, your typical ground surface is going to be what? It's going to be, it's... And what happens? Well, you get, when it rains, what do we get? We get ponding in various places, and it sits there, and it may dry out, and then we have another rainstorm, and maybe after about 10 rainstorms, what happens? The water sits there, and then it eventually seeps through. It sits in our puddles, for instance, and ponding, and it seeps into that clay after an amount of time, and the clay can become saturated. So it's after many rains, the clay can become saturated, and we can have the same problem with the clay. So just be aware that the clay is not immune for it. We like our gravel because that's generally not going to cause us a problem. But if the soil is clay, silt, fine to medium sand, then the water can build up in our slope. So 2 things: water in your slope, water behind your retaining wall can cause problems. And these are the reasons why, as I just went through. Okay, we'll stop there.